This is Dr. Russ, and we're going to go through the 5 steps of hypothesis testing, including the changes that we have for working with correlations. Just a quick note, in these slides and the lecture, the interpretation part of the problem that you'll see at the very end of the 5 steps is sometimes referred to as required for all the problems and sometimes referred to as a bonus. So please refer to whatever the instructions are for your semester to know how to approach the interpretation, whether you should include it in all your problems or whether it's a bonus. Typically, it's required for all the problems. So in this example, I'll go through each of the 5 steps and talk to you about how they differ from what we have done in the t-tests. So parse the problem is going to be identical, except that when we come to listing the dependent variable, we're not going to list that anymore because we don't have it. We'll be listing 2 variables, x and y, instead of just one dependent variable. And the hypotheses we can state in longhand, or we can use our shorthand, but instead of using mu for mean, we're using the correlation, which in this case, the Greek symbol for it is rho, which is this p-looking thing, instead of mu. In step 2, we're not actually going to state the comparison distribution anymore. Instead, we're going to use this step to create a scatter plot and predict the Pearson R value. So we're going to use those skills that we have developed and guess the correlation. We're going to use them here to actually plot out and predict. And this is an excellent practice because it helps you to know if you come up with a correct conclusion. Next, you're going to look off the cutoff point. And we already talked about how this is actually a t-distribution that's been extrapolated to all of the possible correlations depending on how many are in the sample. And so on the previous slide, you have seen what this looks like. Actually, no, this is what it's going to look like. It's a little bit different tool. So what you're going to see, it's really tiny here, but you'll see it in other lectures. You're going to get all kinds of cutoff points, the t-score, the z, the chi-square, the f, and then way down at the bottom here is r. And when you enter the appropriate data, which is degrees of freedom and significance level, you're going to calculate for the cutoff point, and then you're going to have to scroll back down again to here in order to see what that cutoff point is. Next, you're going to calculate the sample R-score, and you can see the formula written here again. It's just the average of the sum of cross products. It's the average of the cross products, I should say. And then finally, you're going to decide and conclude. We have a little bit of an extra step at the end here, so you'll make your decision in the same way, drawing on the distribution. And your conclusion, once again, it'll be a nice, easy statement to write, and you'll end with a statistic. And then you're going to interpret it. And so if the result is significant, you have to discuss the plausibility of each of the 3 interpretations, the expected cause effect, the reverse cause effect, and the third variable. So the example is we're going to test the hypothesis that there's a significant positive relationship between points on the midterm exam and the final exam in statistics. Use alpha equals 0.05. And so here we have data. I only listed 8 students, but these are students from last semester. And these are midterm exam scores and final exam scores. And these are points, not percents. These are just points out of the total possible. And these are the actual scores. I wrote 2025 here, but it's actually 24. And that 20 total students completed the course. I only showed 8. So these are the kind of data, these are what the data look like and what we'll be working with. So in this example, we are going to test the hypothesis that there's a significant positive relationship between points earned on the midterm exam and points earned on the final exam in statistics using alpha equal to 0.05. And we'll start by parsing the problem. So population 1 is just going to be students or people like those in our sample. And population 2, people for whom there's no relationship between the two variables. Maybe they're just two random variables pulled out of the air. We're going to have the x variable, the midterm exam, and y will be the final exam. It's one-tailed high, and I can tell because of this word positive relationship. I have the hypotheses here stated in abbreviated form, but you could also write them out. So H1 in the abbreviated form, we're now not using the mean anymore, we're using the correlation, and we name that in Greek terms as rho, which is this p-looking symbol. And so the research hypothesis is that rho is greater than 0. The null hypothesis is that rho equals 0. We could also state the research hypothesis as there is a significant relationship between the variables, and the null hypothesis that there's no relationship between the variables. And so that's step 1. And let's continue to step 2. Create and predict is how I've abbreviated it, but it means to create a scatter plot. So take the data points and plot them. You can do it by hand, or you'll see how also to do it in Excel. And so you'd get something like this. And then we need to predict or estimate what the Pearson R value would be. And so let's draw that line of best fit in there. And I'm going to place it right there. And I'd say it's going to be 0.45. And you can see how I wrote it. Our estimate is approximately 0.45. That's just my estimate or prediction based on this distribution. And now we continue with steps 3 through 5. So in step 3, we look up the cutoff point. We're using the cutoff calculator tool that we'll demonstrate in class. And as you know, you need the degrees of freedom, which is n minus the sample size n minus 2, minus 1 for each of the two means we calculated, which means minus 2. And in this case, we had degrees of freedom equals 18. Alpha was stated at 0.05. And I went ahead and looked that up. I can't jump out of this slide to do that in front of you. But I did look it up, and it's 0.378. And here is the distribution we're going to use. And you'll remember that this is really going to be a t-distribution extrapolated to the Pearson R coefficients calculated by the mad scientist. And so we're using that tool here. And we can plot the cutoff point here. Ralpha equals 0.378, one of the few times in your lives you'll be able to say that. We can shade the tail of the distribution, looking for the significant reason, and mark in the center the fail to reject region in the center of the distribution. And continuing on, we can calculate the standardized sample score, which in this case is the Pearson R score. And so the R sample score, I already did the math. And of course, you'll be doing the math, but we'll do that in a different lecture. And we have a 0.581. And so we can see that this 0.581 falls within the shaded region of the distribution. We make the decision the same as always. Because it's in the shaded region far in the tail of the distribution, we decide that we can reject HO and conclude that a significant positive relationship exists between midterm exam scores and final exam scores. And of course, since it is significant, we have to do an interpretation, which you'll see on the next slide. This last page looks at how to interpret significant results, explaining causal possibilities for any results that are significant. If you did not get a statistically significant result, or if you did not reject HO, you won't be doing it for this problem. But all the others, you'll be doing this interpretation as well as the concluding statement. So possibility 1, expected cause effect, X causes Y. In this example, it means that higher or lower points on the midterm exam cause higher or lower points on the final exam. It's written this way because higher points correspond with higher points, lower correspond with lower. This could also be, of course, if it's a reverse. If it's a negative correlation, this would be the opposite. But we want to indicate that this goes in both directions. And we have to tell whether we think it's plausible, and I think this one is. I think this could happen. It might work like this. Maybe people who score high on the midterm exam find themselves feeling excited or proud or motivated, and this leads them to work hard. And so they also score higher on the final exam. Possibility 2, the reverse cause effect, y causes x. This would mean that higher or lower points on the final exam cause higher or lower points on the midterm exam. I find this one to be not plausible because the final exam happens after the midterm exam, so it's not possible that the results on the final exam could cause some sort of impact or difference in scores on the midterm exam. So anytime the y variable comes after, in time, the x variable, you would have to find it not plausible because we can't reverse time. Possibility 3 is that a third variable, unknown variable, causes both x and y. And in this case, it would be an unknown variable causes both higher or lower scores on the midterm exam and higher or lower scores on the final exam. So one factor that systematically causes both of these. And I'd say this is definitely plausible. And of course, I would have to name such a factor, and a factor like math confidence could impact both scores, like people who are more confident would have higher scores on the midterm and higher scores on the final, and the reverse is true as well. And so this is how you're going to be doing the interpretation, and wording is very important. So when you write these out, you can't be careless with your language. You have to write out all of this. You have to write out expected cause effect, x causes y. You have to write out this second sentence, what that would mean in the given problem, and then you have to tell whether it's plausible or not and why with an example. And so you do need to do this whenever you're doing an interpretation, and you need to be careful with your words. And that's the end of this lecture.